Hello everyone, my name is Noémie Cohen. I'm doing an industrial PhD between Onera and Airbus. To begin, I would like to talk a little bit about the new machine learning based aeronautical safety standard. These are guidelines like rules for integrating machine learning technology into aircraft systems. And roughly speaking, it states that one of the objectives of this new standard is to ensure that the machine learning model preserves its intended outputs under perturbations to its inputs. And this gives us an idea. And I'm really excited to share with you our work on verification for object detection. First, I will begin with the context, followed by our contribution. You may be familiar with multi-class object detection, which aims to detect objects within an image. Detections are composed of three elements: a bounding box, a rectangle encapsulating the object of interest, an objectness score, also known as confidence score, and a class. And in our study, we narrow our focus to single object detection, dealing with only one bounding box, the one with the highest objectness score, and one class, runway. Essentially, we are focusing on vision-based landing. And here are the results of a model trained by Geoffrey Delhomme for vision-based landing, demonstrated at an accelerated pace. The state of the art involves using trained neural networks. And for example, here we have an image as input and a bounding box as output in purple. Our problem is that neural networks are sensitive to perturbation. And for instance, let's consider this initial image where the model predicts correctly. The removal of some pixels, perhaps due to camera failure, could cause the neural network to fail. And for example, this issue also arises with image rotation. So our problem is that neural networks are sensitive to perturbations. Here we consider natural perturbation as plausible perturbations. And our question is, how do we quantify the impact of a range of perturbations on a correct prediction? Our objective is to use an automatic and sound method, and our strategy is to use formal methods. What we aim to achieve is this. By applying a range of perturbations to an image, we want to ensure that the output is well localized. But what does well localized mean exactly? There are many methods available, but the most commonly used metric for bounding box localization is the intersection over union. It is a value between 0 and 1 that evaluates how similar two bounding boxes are. Thus, we take our purple predicted bounding box, B0, and check its similarity to a ground truth bounding box, BGT, known to be accurately placed around the objects. The calculation of the IoU is the following. It involves computing the area of the intersection between the predicted bounding box and the ground truth, divided by the area of their union. So for instance, the area of the intersection is 1, the area of the prediction is 6, and the area of the ground truth is 9. Finally, we obtain an IoU value of 1 over 14. The key takeaway is that the IoU is a metric for bounding box accuracy. If the prediction overlaps accurately with the ground truth, the IoU is close to 1. If there is no intersection, the IoU is 0. And if there is only a bit of overlap or if the predict box is imprecise, then the IOU is near 0. We can define our goal more precisely. We want to apply a range of perturbations to an image and then ensure that the IOU of the output is above a threshold T. So let's consider two strategies. An enumerative approach that is possible because pixels values are integers, and a non-enumerative approach. And let's apply it to two perturbations. First, let's begin with the brightness perturbations. We take the initial input image, as we have already seen at the beginning, and apply to it a uniform brightness perturbation range. It is defined thanks to a coefficient alpha that is within an interval from alpha min to alpha max, here between -7 and 7. Please note that until the end of the presentation, I will use this notation with a line under and a line above to represent an interval. Thanks to this, we can define a perturbation domain. The perturbation domain corresponds to all images that have the same size as x0 and where we uniformly apply an alpha coefficient. In this perturbation domain, there are 14 images. This number is independent of the number of pixels. Indeed, we can set up a little pipeline. Each time we take an image from our perturbation domain, we perform an inference on our model, obtain a predicted bounding box, compare it to a ground truth, and then calculate the IOU. For the sake of clarity, we will denote Z0, Z1 as the bottom left and Z2, Z3 as the top right corners. And this coordinate represents the bounding box B0, defined by Z0, Z1, Z2, Z3. And we can do this for each of our images in our perturbation domain. In the end, we obtain the whole values for the 14 images in the perturbation domain, and we can bound our IOU between a minimum and a maximum value. Note here that the IOU is neither convex nor concave. Here the minimum value is 0.22 and the maximum value is 0.98. And if we want to check our property, is the IOU on the output above a threshold T equal to 0.5? And since the lower bound is 0.22, then the property is not verified. So in this case, for this brightness perturbation, an enumerative approach can be desirable to solve our problem. But let's consider another perturbation, a white noise perturbation. So we revisit our initial image and apply a non-uniform white noise perturbation defined thanks to the epsilon coefficient equal to 7. The perturbation domains corresponds to all images that are at a distance epsilon from our initial image. And for example, this image is within the perturbation domain. In this case, the perturbation domain contains 7 to the power of k images, with k the number of pixels. For a very small image of 300 pixels, it contains more to 10 to the power of 200 images. Wow, that's a lot. So using an enumerative approach here is impracticable because it will take several years to compute all the reachable bounding boxes. So an enumerative approach can be desirable to solve our problem, but not always. And abstract interpretation is another method that can always solve our problem. And with this non-enumerative approach, we compute the problem for the white noise perturbation. So this time, we define an abstract domain. It is another approximation where pixels' value are floats. And for example, we can use an interval abstract domain. Then we can establish another pipeline. Let's take an abstract domain as input and a ground truth, and use some abstract interpretation solvers, such as ERAN, Decommon, Autolirpa. Thanks to these abstract interpretation solvers, we can obtain the set of reachable bounding boxes quite quickly. And here it is an over approximation. Each coordinates are not represented as single data points, but as intervals. And in order to verify our property, the goal is to bound the IoU. But so far, nobody has done such a work. And that is our contribution. The key takeaway is that the goal of our contribution is to bound the complex IoU function given a set of reachable bounding boxes. So let's deep dive into our contribution. The key takeaway from this slide is that we have developed two methods to solve our problem. But before we delve into them, let's do a quick recap of what we have covered before. In the enumerative approach, we compute bounding boxes for each image in the perturbation domain, calculated the IoU for each, and finally bounded out the IoU, and we obtained, for example, 0.22, 0.88. Now, with abstract interpretation, instead of having many bounding boxes, we work with a set of reachable bounding boxes. And we aim to compute an IoU for the set and then bound it. We have developed two methods to address this challenge: vanilla and optimal. Vanilla serving as a baseline. So now let's focus on the first method. The key takeaway is that vanilla uses interval arithmetic to solve our problem. And essentially, vanilla bounds the primitive operators. After bounding, we performed subtraction, addition, division of interval, which then provide us an interval. And we are satisfied because we have our bound on our IoU. But here you might wonder, okay, but how do we bound each operator? And let's look at an example. So consider the area of the predicted bounding box, defined as the length on the x-axis multiplied by the length on the y-axis. It is the area of a rectangle. However, our coordinates are not single data points, but intervals, thus requiring interval arithmetic. Then we proceed with the subtraction operation between these intervals, and finally the positive multiplication operation. In summary, by using interval arithmetic operations like addition, subtraction, multiplication, division, finding maximum, minimum values, we can obtain our final bounded IoU. But this is an approximation. And then we ask, can we do better? And that's why we have developed a second method. Optimal is a method that uses partial derivative to solve our problem. The idea is to ask, can we find within the set of reachable bounding boxes the box that minimizes and maximizes the IoU? When we find these two extremes, we compute the IoU for each, obtaining our range of IoU values. Again, I guess you are thinking, okay, but how do we obtain the maximum and the minimum? And here we use partial derivatives to do it. So let's take, for example, the coordinate z0. There are two cases when z0 is lower or higher than z0 gt, the coordinate of the ground truth. And for these two cases, we derived and obtained a positive and a negative derivative. It reflects an IOU that increases until it reaches the ground truth box and then decreases. And an important result is that this behavior holds regardless of the value of the other coordinates. And thanks to this, for example, for the maximization, we need to find the value closest to the ground truth coordinate for each coordinate. If the ground truth is within the interval, we simply choose it. If it's on the left, we take the lower bound. If it's on the right, we take the upper bound. And with this strategy, we can obtain an exact IOU value for each bound. So to sum up, from an abstract domain and a ground truth, using abstract interpretation solvers, we obtain the set of reachable bounding boxes. And thanks to our contribution with vanilla and optimal, we can effectively bound the IOU. Let's see the results. First of all, the complete pipeline is available on GitHub. If you want to experiment, you can find tutorial on the tutorial folder on GitHub. The model is trained on the large dataset, which contains images of landing approaches at runways. For the moment, the perturbations already implemented are white noise, brightness, and contrast. However, during the course of my PhD, I would like to tackle geometric perturbations. The abstract interpretation solver we use is AutoLIRPA. We implemented manually brightness and contrast ourselves using this tool, so you can benefit on it on GitHub. And we have conducted several experiments. The lab dataset divided its images by the concerned airport. We randomly selected an airport and chose 40 images accurately localized by the model without perturbation and conducted 200 experiments per image. We use 11 different ranges of perturbations, 3 methods to obtain the set of reachable bounding boxes, and then our IOU computation methods. I will not present all the results here, but I will focus just on one image perturbed with the white noise perturbation with crown methods, and of course our 2 methods. So the key takeaway of this slide is that we can solve our problem using this pipeline. In fact, we normalized an image and apply a perturbation shown on the x-axis. And on the y-axis, we show the bound on our IOU. Without perturbation, the IOU is a single data point, equal to 0.92. The more we perturb it, the wider the IOU bounds become. In red, it is optimal. In blue, it is vanilla. And we can see that vanilla is an approximation and that optimal bounds are tighter. For example, looking at the perturbation of 0.0008, the minimal bound given by optimal is 0.5, and the one for vanilla is 0.3. Okay, but now let's see our problem. The question is the IOU on the output above a threshold T of 0.5. Thanks to Optimal, we are 100% sure, like we can guarantee, that the model is not sensitive to this perturbation. Indeed, we can solve our problem using this pipeline. So let's summarize what we have learned today. The goal was to take an image, apply a range of perturbations, and ensure that the output is well localized. We have learned today that the IoU is a metric for bounding box accuracy. That abstract interpretation can always solve our problem. The goal of our contribution is to bound the complex IoU function given a set of reachable bounding boxes. We have developed two methods to solve our problem. Vanilla, that uses interval arithmetic, and Optimal, that uses partial derivative. And our pipeline is available on GitHub.